in this presentation, we're going to talk more in depth about covariance, some basics, how we use it in the PC calculation, about one slide on that, how it's generated, specifically the covariance that comes with our ASW solutions from the CSPAC, how it's propagated, because you get your covariance at your OD epoch, but then you need to propagate that to your time of closest approach. How do we tune the covariance to make sure it's realistic? And then a little bit about covariance compatibility. All right, so just to get some background before we really jump into covariance, talk about OD solutions. So the purpose of an orbit determination is to generate an estimate of an object state at a given time. And that's the epoch time. And then you also want to generate other parameters that allow you to take that estimated state and propagate that into the future, predict where that state might be in the future. And that's our orbit propagation. And so then you want to have a statement of your estimation error, because we know we did an estimation of what this orbit is. So there's going to be some error about that. And you want that both at the epoch, but also propagated forward, for what we're doing in CA, so we can have what our uncertainty is at TCA. And so this is usually accomplished by the means of a covariance matrix. So that's where we get into covariance. So the covariance matrix is kind of summarizing all of the uncertainties in the estimation process for your OD. And so what could those errors be? So when you do the OD, whatever method it may be, for ASW, it's a batch method. That presumes that the systematic errors in the estimation process are solved for. And therefore, the remaining errors that are there should be Gaussian in nature. So sometimes we know where some of the uncertainties are coming from. Maybe it's uncertainties in our atmospheric drag predictions. But sometimes it's not very clear. And so that we'll talk about there could be intentional inflation of the covariance, for example, to accommodate uncertainties that we don't necessarily know the source of. Regardless, we are presuming that they're Gaussian and unbiased, and this becomes important for formulating our covariance matrix. So for the ASW OD solution, what do we get from that? We have state parameters, so we have the 6 state parameters, position and velocity, whether in Cartesian or in the element space. We also solve for non-conservative force parameters, so this is specifically the ballistic coefficient, which is how much the spacecraft is susceptible to drag, and also the solar radiation pressure, how much the spacecraft is susceptible to radiation momentum from the sun. So that's 8 parameters that we're going to solve for in the OD solution, and they're going to have associated errors with that estimation. Additionally, and we'll talk about this more towards the end of the package, the ASW solution also has considered parameters. So the ballistic coefficient and the SRP are also a considered parameter, so some a priori information about those parameters is used to change the OD solution to accommodate errors that we know about but can't address within the OD. And so it might be a little confusing. We'll come back to that with a few slides at the end. We'll talk more about the considered parameters. But yeah, essentially what to think about is that we have 8 parameters about our OD that we're estimating, and we have some uncertainty about them. So how do we actually model this OD uncertainty? We have all these different states, and in general, we would need these 4 moments, the mean, variance, skewness, and kurtosis, to describe that distribution for each of those states. However, because we made our handy-dandy Gaussian assumption about these errors, we can actually ignore the skewness and kurtosis and just use the mean and variance to describe how the error is for the different OD components. So the error distribution can be expressed by means of variances of each solve-for component and their cross correlations. And so therefore, our error can be fully represented by means of a covariance matrix. And this is what that looks like in a generic form. You have the variances along the diagonal, and then your covariances here, which are this is a symmetric matrix. And for what we're doing in CA, you can imagine this matrix is actually your RIC matrix. And if you took the square root of this upper left box here, you would actually get the uncertainty about your radial component. And so on the CDM, you actually get the individual object covariance matrices. And you could actually do that calculation by hand and find what the individual object radial in-track and cross-track uncertainties are. Here's what that covariance matrix looks like. You've got in yellow here, we're highlighting the position covariance. With this is the RIC diagonal. You would also have the radial velocity, in-track velocity, and cross-track velocity down here. And then over here, you have your ballistic coefficient and SRP uncertainties. For the ASW, SRP is referenced as this AGOM acronym. So for most events, we actually do get this 8x8 matrix. For a lot of objects, though, it's only a 7x7 because SRP is not always solved for, depends on the orbit regime of the object. Kind of reaching back to the previous presentation, because we have this one large matrix that has units of meters, meters per second, and also meters squared per kilogram, this matrix is kind of unstable. Small changes to any of these numbers could cause the matrix to be non-positive definite. And that's why truncation or interpolation errors can be so important, because these numbers vary so wildly. You have something that's 10 to the 5th, but also 10 to the minus 7th. And so small changes in these different values could cause this matrix to be non-positive definite. And because of that, we often like to work with just portions of the matrix. So thankfully, for the 2D PC, we're just using the 3x3. We can consider that separately, and it's going to be more stable. All right, so here's kind of notionally what the covariance ellipsoid would look like that's described by that covariance matrix. So we have the radial, in-track, cross-track components described, and you have this error ellipsoid now about your object. And we saw that also in the probability collision presentation. We took this and we projected it into the 2D plane. So here's your position covariance defining your error ellipsoid. It's centered about the spacecraft position. And again, if you take the square root of the variance for each direction, that's defining your semi-major axis of the ellipsoid. The off-diagonal terms, we didn't talk about those too much, but those are going to rotate the ellipse from this nominal position. So that would actually change the orientation of the covariance ellipse. One thing to note is because we're not using a univariate normal distribution that most people are used to when we talk about Gaussian distribution and how much of the sigma you have. In this case, the 1 sigma ellipse is capturing about 20% of the expected data points. So that's a lot lower than for the univariate distribution, which is, I think, like 68%. and then 2 sigma 74, and 3 sigma about 97%. So having this 3D ellipsoid is not necessarily capturing as much of the expected states within 1 sigma as maybe we're used to thinking about. Okay, so how do we use covariance in the PC calculation? So going back, some of this should look familiar. Here you have that primary and secondary combined covariance ellipse projected into the 2D conjunction plane. So again, you have the velocity going into the page in this case, and your primary at the hard body radius, or at the missed distance encapsulating the hard body radius. And so again, the PC here is how much of this covariance ellipse falls within your hard body radius. So main takeaway, covariance is absolutely essential to calculating probability of collision. We couldn't do it if we didn't have the covariance. And also, to get into further why we need covariance and don't want to rely solely on missed distance to make decisions is because there's poor correlation between the PC calculation and the missed distance. So these 4 lines on the CDF plot here are different PC ranges. So the blue here is your highest PC range from 5 × 10⁻⁴ to 5 × 10⁻³. And then in red, you've got 5 × 10⁻⁵ to 5 × 10⁻⁴. Down here, you have the missed distance. So the idea is, as you're going out, getting larger and larger missed distance, how many events are falling within, in this case for the red and blue, pretty high PC bounds. And we see that even up to 10 kilometers, you can get a fairly elevated PC value. Not so hard to imagine for some very tiny missed distances that you can get large PCs. But so this is why it's important that we calculate PC when we think about covariance, because you can get a wide range of PC values for a wide range of missed distances. And so it may not be enough to say I'm 1 kilometer away or I'm 5 kilometers away, I'm safe. The PC calculation using the covariance may tell us otherwise. Okay, so talked about covariance. We have the matrix. We define that. How is it actually generated for our ASW information, and then how do we propagate that to TCA? So as I mentioned, the ASW method, so this is what the CSPOC is doing. That's the information that we get for the majority of secondaries and also for our primaries, although we also have the data using the owner-operator information for the primary as well. So when the ASW batch least squares method does an OD update, it's going to be using a minimization equation to try and find the best fit. And the most important piece here is this W matrix, the weighting matrix. And that's going to provide information about observation quality from the different sensors that track the object. And that observation quality is going to affect your covariance. So we'll talk about that. And in fact, this term, A transpose WA inverse, up here in this equation is your covariance. The other terms here, the A matrix is allowing you to map your residuals, and this B vector is your vector of residuals. But for the covariance, it's really impacted by the W matrix or the weighting matrix. So let's talk about that a little bit, because this is the main thing that's going to impact the uncertainty that we get for our ASW solution. So it's an a priori covariance because the covariance matrix itself is not containing actual residuals. The residual is that B vector, which doesn't show up in this portion of the equation. So what's interesting is that the covariance matrix here is a function of the amount of tracking, the times of those tracks, and the sensor calibration relative weights among those tracks. And that's what the weighting matrix is actually defining for the different sensors, like what the sensor calibration weights are. And so what's of interest is that it's not a function of the actual residuals from the correction. It's the a priori estimate of what those residuals should be for a track from that sensor. So for every track for an object that you get from a sensor, it's going to have the same weighting to it, whether or not a particular track was more degraded than another one. So that's kind of interest, and certainly an area of improvement in the future, although that's out of what CARA does, because this is the OD done by the ASW system. It does pretty well, but it's not going to account for unmodeled errors, such as what happens when you have atmospheric density error predictions. And this matrix is only as good as the sensor calibration process. So if the sensor hasn't been well calibrated, that's going to be carried into your covariance matrix. So yeah, certainly room for improvement, but it's good that we can understand what's going into the covariance matrix. Okay, so you get your covariance matrix at the OD epoch. Now you want to propagate it to TCA, so you can do your PC calculation. There's two methods we're going to talk about. The first is a full Monte Carlo. So what we talked about before, you're going to have your covariance at epoch, draw states from it, propagate those out to your TCA, and that's going to then represent your covariance at TCA. And that's going to, because it summarizes statistically what the end states, where they are at TCA. So it might take a lot of time to do that, and there's over 20,000 objects that have ODs updated at least 3 times a day by the 18th. So perhaps the Monte Carlo method is not going to be fast enough. So what do we actually do for the ASW solution? It does something called linear mapping. So we know that orbit propagation involves nonlinear dynamics, but we can linearize them and actually really be able to propagate quickly our covariance. And it uses a straight state transition matrix to do that. One issue with this is that these linear approximations eventually are no longer going to be valid. What we've seen is generally for the times that we're propagating across, they're not long enough to invalidate the linearization for this propagation. And we'll talk more about process noise, but if the covariance is being propagated and it's seen to be not actually modeling the uncertainty of the situation, it's too small perhaps, then you can use something called process noise to inflate that, to actually encapsulate your actual errors that you're seeing. And so we'll talk about that more when we talk about how to improve covariance realism. So just to summarize, Monte Carlo is going to be more accurate, but it's going to take longer, and linear mapping is going to be a lot faster, but then it's going to be less accurate. You're going to need a priori information to do that, and you may have to use process noise, which isn't something you can just turn on and use. That has to be tuned as well. So it's going to be a lot faster once it's implemented, but there may be more tuning at first to get that working. But yeah, and linear mapping is what's done with the ASW. Yes?
Maybe when you use the state transition matrix for linear mapping, you start with an ellipsoid, say an arrow ellipsoid. When you map that forward, you get an arrow ellipsoid. So with the Monte Carlo, you start with an arrow ellipsoid, and you end up with a collection of points. So with the arrow ellipsoid at the end, you can characterize it with the dimensions of it or whatever. How do you characterize this collection of points?
You may want to repeat the question for the microphone.
Yeah. So the question was, when we propagate with linear mapping, We're actually propagating the whole covariance matrix forward, so it's defined. How do you do that with the Monte Carlo, where you really just have this collection of points now at a future state? How do you characterize what the covariance matrix is? So I don't know that I have a good answer for you on that one. I think based on this bullet here, you would have to do a statistical analysis of those data points and find like what the distribution is, and then you could define the covariance matrix from that.
That can fit in the website too.
Yeah, yeah, okay, cool. Okay, so as I've hinted at, you may have to tune your covariance. How do you know it actually represents the uncertainty that you really have in your state or your propagation? So when we do collision assessment, it's important that the covariance, and in particular the position covariance, since that's what we're most often using for our calculations, be a realistic representation of the state uncertainty at the propagation point of interest. And so having a covariance ellipsoid that's much smaller than your actual error or much larger than your actual error, in both cases, we don't want that. We want the most realistic representation because you could either get an inflation or a dilution of the PC if your covariance matrix is too large or too small. So how do you know whether your covariance is realistic? There's kind of two things to think about. Is it conforming to a trivariate Gaussian distribution? And if so, does it have the proper dimensions and orientation? So I was talking about proper dimensions when I was talking about the size of the ellipsoid. So what happens if you have non-Gaussian error volumes? And this could happen if you're propagating for a longer time, your linearization is starting to break down, and now your error volume may actually become non-Gaussian. If you can maintain your volume in element space, we've been talking a lot about how using the equinoctial space is really useful. That could be one way to resolve the breakdown from the Gaussian, but also we've just found that it doesn't occur that often that you actually have non-Gaussian covariance. Unfortunately, when it does occur, it can significantly affect the PC, so it is something we are interested in. The remediation we really have right now is to look at Monte Carlo in element space because we know that that's preserving that Gaussian nature. So what we don't really have right now is criteria for when you have non-Gaussian issues. And so, you know, in operations, if you can have some kind of flag that tells you, hey, you need to run Monte Carlo for this event, that's where we're still working on that. So we know it can be a problem. We know how to solve it. So we're just working on the middle portion of when does this problem arise? But in general, it's not the main kind of issue that we face with covariance tuning. More often, what happens is, and missions are getting a lot smarter as covariance has become more commonplace, but sometimes you have maybe just the covariance that comes out, the generic thing that comes out of the OD software. This is the default covariance. You attach that to the state that you provide, and what happens is then you have a non-realistic covariance matrix. So how would you go about tuning that? What you need is the position differences between a predicted ephemeris and a precision position, so it could be a definitive ephemeris or some kind of reference orbit. And you're essentially just going to look at how far off is my actual prediction to what really happens, or to this reference orbit. And so then you can construct a covariance matrix that encapsulates the differences between those two states. So this this has been done by a number of missions and isn't too difficult. But this is kind of just telling you whether or not your covariance is realistic. So if it turns out, oh, actually my covariance is not encapsulating the difference in what I'm actually seeing. I'm predicting that I'm 100 meters off, but I'm consistently 200 meters off. How do I capture that in my covariance matrix? So that's where covariance realism can come into play. So we're going to talk about scale factor computation, process noise, and consider parameter. This is the consider parameter we talked about in the beginning in ASW, and how those can be used to improve your covariance realism. All right, so scale factors, pretty straightforward. Is used actually for the ISSCA. They do scale factors on their covariance. You would also look at historical data. How different are the states that we're getting? And one thing I didn't note previously is that you are tuning for a particular propagation state. So whether it's 1 day to TCA, or 1 day of propagation, or 3 days of propagation, you can't have an ideal covariance for all times because how the covariance evolves change over time. So you kind of have to pick a sweet spot where you want the covariance to be the most realistic, which is not to say it's like totally not realistic at the other time points. It's just it's tuned to that one time. And usually somewhere around 1 to 3 days is where people might tune their covariance, particularly for CA, because that's when we're starting to get really interested in maybe remediating an event is around that time. Okay, so how do you apply a scale factor? You've looked at kind of historical data and then essentially find a value that you can multiply your covariance by, so now it's encapsulating your actual error in your orbit. And in that case, it's just a single scale factor. The entire matrix is multiplied by that one number. So it's essentially like inflating all axes of your covariance matrix equally. You could also use a diagonal matrix so that each of the 3 axes is changed in a different way. And that actually may be more appropriate because usually your covariance isn't wrong in the same way in all 3 axes. We tend to have the most error in our in-track. The cross-track tends to be really well known for most objects, and then radial is kind of in between. So that's one thing you could do is actually have different scale factors. So at JSC for the ISS, this is an offline analysis that's done and updated for each event that they're doing. So it may or may not be appropriate for all like ops concepts that people are doing. But also for just a primary object, like this is being applied, I think, also to secondary objects. But if you're just interested in your payload, then you could have a set scale factor that you use for a longer period of time. Okay, getting back to process noise, touched on this briefly. Used most often with some kind of sequential filtering technique. It's really just at the highest level a way to also kind of inflate your covariance. As it turns out, covariance tend to be too small rather than too large. Although you can get covariance matrices that are quite large. If you've ever done launch COLA, there's a case where you have really large covariances, and that's actually accurately describing the uncertainty of the launch situation. But it does make CA difficult because it deflates pretty much every PC because your uncertainty is so high. But for most stuff, we're kind of undersized. So something like process noise, where you have an iterative approach rather than doing some kind of historical data, you can look at the acceleration variances that you're getting at your OD, and then use that to define this Q matrix and use, again, a state transition matrix to propagate it forward. One thing that's nice in contrast to the scale factor is constructed this way. It shouldn't be as tuned to a certain time of propagation. It should work better across all propagation states. So that's definitely a bonus for the process noise. So what do we do for ASW? How does it account for unmodeled estimation errors? So the ASW uses consider parameters, which are kind of similar to the scale factor. But the process is, first they're going to take, the system's going to take an unaltered covariance. So the VCM, or the vector covariance message, has the OD information at the OD epoch. And then it's going to scale that covariance by the weighted RMS if it's greater than unity. So that's the WRMS. It's on the summary reports. So it's multiply the covariance matrix by that. Little specious, I guess, whether that's a good idea. But it was an early attempt that's still used to improve the covariance realism, as it was identified that the covariance matrices were undersized for ASW. Yeah. From the OD, of the residuals from the OD, yeah. That's what the weighted RMS is. So that's the first thing they're going to do. Okay, here's where the consider parameter for the ballistic coefficient variance comes in, and we'll talk about how that's determined. But that's also being applied now. So this is the location in the covariance matrix. If the SRP has some variance, then that may be added. Right now, that's not being used. And so now, between these two consider parameters that have been added, we can propagate this now altered covariance using the linearized dynamics. And then that matrix, it's an ASW, they actually propagate natively in equinoctial, and it then transforms to Cartesian when the data is then output on the CDM. But the idea for the two consider parameters is to account for uncertainty, unmodeled uncertainty. And so here's where the ballistic coefficient uncertainty is that actually gets multiplied back into the covariance matrix. So it's kind of interesting, even if we weren't using that portion of the matrix, we're just using the 3x3 position matrix, we're still being affected by what the ballistic coefficient consider parameter is, because the entire covariance matrix is being modified by that value. So that's kind of interesting. So how do they come up with what the dynamic consider parameter, which is based on the ballistic coefficient? But the DCP is attempting to account for poorly modeled atmospheric density and also frontal area variation in a space in debris objects or spacecrafts. So for the atmospheric density forecasts, we're going to be looking at the satellite height and the geomagnetic activity to figure out what the DCP is. And this was done on a historical set, using historical data. They looked at different objects from different altitudes and during different parts of the solar cycle, because that affects atmospheric drag a lot. And we're able to come up with different values that can be used. And we'll see a chart. Basically, you pick a value off a curve that gets used for the DCP to multiply back against the covariance matrix. And then the second part is that frontal area variation. So that's going to try and account for objects that might be tumbling. They're presenting different frontal areas. Their ballistic coefficient value is changing. And so we need to account for that in our covariance because as that object is rotating, the drag effects and how its state changes may not be well modeled by the covariance matrix. So you calculate those two and combine them with the root of the sum of the squares, and you get a bunch of values that you can pick from. So this is actual ballistic coefficient consider parameter values so we don't have what the actual values are, but these are the actual curves. And on the x-axis here are the different altitudes. So there's kind of this peak around the 700 kilometers. So basically what it's saying is pretty much everything above 400-ish kilometers was pretty undersized for most cases because this value is going to serve to inflate the covariance. And then as the AP increases, and over here they're actually using the DST, again this value is increasing. So the higher the AP, the more geomagnetic activity, the more uncertainty in our atmosphere, the more inflation of our covariance to deal with that, essentially. We're more uncertain, so we're going to inflate our covariance to cover that. And so on this chart, just looking at what's a bigger effect, is it the atmospheric uncertainty or the frontal area uncertainty? For about 90% of objects being tracked, the density forecast error is much larger in blue here than the frontal area variation. For a minority of objects, you do have the frontal area variation being a bigger issue. So really draggy objects, hard to kind of understand what their future position is going to be. Okay, so that kind of covered how we can improve our covariance by using scale factors or the process noise or the consider parameters used by ASW, just similar to a scale factor. I have one more slide. This is the covariance theory compatibility. And talking about this because in CARA we developed, we call our ASW synthesized covariance. We have a number of missions that aren't able to provide us with covariance information that leaves us in a tough spot, particularly if they have a maneuver planned, because the ASW-OD does not model maneuvers. We need to use the owner-operator ephemeris in order to evaluate post-maneuver events. So how do we do that if we don't have covariance to calculate a PC? Hopefully I convinced everyone that's important. So like I said, we actually developed something called our ASW synthesized covariance. And it takes historical ASW covariance for the primary and is going to apply that to the owner-operator state. So, so that's a little background. Discuss whether or not we should really be doing that. So covariance and propagated covariance is a product of the OD that you did to get your initial state uncertainty, and then the propagation of that how you actually propagated the covariance. So it is important then that the covariance be generated from the same OD basis that produced the state estimate. So maybe we shouldn't be doing that. Okay, so our hand was kind of forced because we don't have a good way to calculate PC. We did a lot of test comparisons, and we found that for a vast majority of cases, the PC that we get using our synthesized covariance is very close to what we get with an owner-operator provided covariance. And this is because, in general, the secondary object is most often contributing a lot more of the overall uncertainty of an event than the primary. We often know very well where a primary object is. Owner-operators certainly do, but also the ASW solution does as well because they tend to be large objects that can be well tracked. So in those cases, it's not so bad to use this, even though in general, I'm standing here saying we don't really want to do that. And so we're very encouraging of all missions to provide their own owner-operator covariance. And where it does still really show that it's necessary is if we have two well-tracked objects, very small covariance for both the primary and secondary. In those cases, the accuracy of the primary covariance really does come into play. And so while in most cases we're okay to tack on this covariance, there are some types of events where we really wouldn't want to do that. So yeah, having owner-operator tuned covariance is definitely very important. Okay, that was my last slide. So any questions? Oh, I guess I explained it perfectly.